Okay, so it is now exactly 9 a.m. So this means that we are going to start. Good morning, good day, and good evening, everybody. Thank you all for joining our today's webinar with the title How to Optimize Cycle Times in the Automotive Leak Detection. This webinar will have a length of approximately 45 minutes, and there will be a short 15-minute Q&A session afterwards, in which we will try to answer all your open questions that might have come up during the presentation. Before we dig into the topic and take a look at the agenda of the webinar, please allow us to introduce ourselves to you as your presenters today. On the one hand, we have Dr. Philipp Schurig, who has been an application manager for leak detection systems and batteries at Pfeiffer Vacuum since 2020, and who is firmly rooted in the automotive industry. Myself, my name is Jonas Klöß. I'm also an application manager for leak detection systems as well as for freeze-drying systems. And I've been with the company also since 2020. Yeah, we're both happy to have everybody here today. So thank you for joining. And now let's take a look at what can you expect to learn from today's webinar. Today, we will speak about best practices to improve your leak test system. So we will take a look at different options to reduce cycle times. And I think this is something that is particularly important for the automotive industry, because here it usually counts really much what productivity your leak test system has, what's the cycle time, and every second that you can save is worth a lot. Coming with this is just as important the selection of the right vacuum components, because if you have the right components in place and the right setup, this will enable you to achieve additional savings. Also, we will take a look at helium contamination, and we will speak about possible risks and how you can reduce those risks. And also, we will take a look at different test methods. In particular, we will speak about the full or the partial flow testing mode. We will explain the differences and the advantages and disadvantages of each of these methods. Okay, so let's take a look at maybe as a first step at the leak test cycle itself. So when we take a look at a leak test system in the automotive industry, we can say that it consists usually out of 4 main steps that are important. The first one is the pump down. So in the pump down step, we talk about the chamber evacuation. There terms like free volume and surface crate play an important role. And of course, also the individual pumping unit that you are selecting to achieve the evacuation times that you require. Another important part of the leak test cycle is the filling process. So the unit under test and also the tracer gas piping play an important role here. After that, there comes the testing process itself, so the actual leak test, in which we will speak about not only the suction speed of the leak detector, but also of the differences between partial and full flow. Also, there is the option to add a booster pump. All of this we will explain later on. And as a last step, there's a cleanup, which is important as well, regarding venting and helium evacuation. Yeah, so as you can see, these are all the steps of a particular testing method, which you can see here at the top of the slide, the integral vacuum test. And we know, of course, that there are several different test methods in the leak detection technology. But this webinar will focus on the integral vacuum test. And of course, we know also in the automotive industry, there are other methods. So this is something where we are particularly interested in. And that's where we have prepared a small poll for you. So the question that we have for you is, what other methods besides the hard vacuum test are you considering for your leak test system? So let me start this poll real quick for you.
I started the poll for you, Jonas. So
thank you. Thanks, Philip.
Our accumulation measurement, sniffing method, the spraying method, or the bombing method, or in the end others. So which are not one of the 4 before.
Okay, so I see already some answers coming in. Yeah.
So I think we give you 5 more seconds. And thank you for participating here in our small poll. So the results are really interesting. The majority, so more than half of you, are very interested or considering sniffing a good method for your leak detection. The others, the next second most common is accumulation, followed by spraying. Only 2% use bombing so far, and 7% do others. But today, like Anna said, we're talking about the integral leak detection method, and I want to show you some potential where how to influence the pump down time of your system. So we see here a very easy scheme of a system with a part in a chamber connected to a pumping group. What really influences your system or can influence your system is a change of the volume of your chamber, also the material properties of your part or of your chamber, and clearly also if you add something in the piping or in the suction capabilities of your pumping group. And this we will execute in the next slide. So we will first start with a consideration regarding volume change, followed by material investigation, and finished with the pumping unit examples, what can be changed there. So let's start with the volume. When we see here, first an evacuation curve of a normal roots pumping group, let's say a 2000 cubic meter roots pump with 600 cubic meter RVPs in the back, which should target to empty a chamber of 1000 liters. We have assumed or set here 2 different pressure levels, 0.1 millibar is the upper pressure to be reached and 0.02 millibar for the lower pressure level to be reached. This will stay the same through all of the following simulations you will see. We will only change something on the volume like you will see now if we add our part, because in the leak detection process, to test an empty chamber is not really of interest for your customers or for you as a customer. You want to know how fast is the pump down of the process with my loaded part. So when we install a part here, let's say a 360 liter volume is lost or filled with a part, this for sure influence, like you see here, the pump down curve, as we have now a smaller volume available in the chamber, but on the other hand, a bigger surface. This plays a role when we look at the different pressure levels. For the upper pressure level, we have a drastic reduction in time to reach this level, while for the lower pressure level, it's not a real strong influence with this particular setup we have chosen here for the simulation. So only 3 seconds improvement compared to 10 seconds improvement for the empty chamber. So still 640 liters is a lot, which is an open left free volume in the chamber. You can counteract this with installing some filler materials. So to further reduce your free volume, you can install filler parts to reduce, for example, to 328 liter free volume, but you also increase drastically your surface again due to the installment of the filler material. Again, we see here a further advantage for the pump down time for the upper pressure limit, but again also a significantly lower influence on the lower pressure limit. And the question is now, how much will I always receive a shorter pump down when I add filler material into my chamber? Well, the answer is it depends. It depends on the pressure you want to reach. If you want to stay at the upper level regime, which we are showing here, also to add another filler to reduce the volume even further will help you to reduce your cycle time. When you want to reach a lower pressure level, at some point we have a crossing point where the time gets worse for additional filler. You see here 51 seconds for the third curve and now 57 seconds for the last curve. So even worse, like for the empty chamber, what we see here. The influence is in this pressure regime and the additional surface, which will also contribute to outgassing rates. So this is all the simulations you see here are thought or executed assuming that we add up stainless steel filler materials. But it do not has to be always stainless steel because it's rather expensive, even more today. So a material change is also something which you should consider when simulating or trying to optimize your system. It starts not only with the with the empty chamber and the loaded part, because not all of the parts you will test are mainly stainless steel. When we say, okay, let's see here the pump down curve of the stainless steel part is again like what you've seen before. When we now only assume that the red line or the part you test is made out of aluminum, the story looks a bit different. With the change of material, also the change of properties of the part you test change, like the outgassing rate. You see here only a slight decrease for the upper pressure level, as here the outgassing or the humidity on the surface is not the strongest influence still. It decreases here by 3 seconds. But when we look at the lower pressure level, it's rather 50% more time, 53 seconds versus 75 seconds. This is nothing you can really influence on your own. You have to consider this when initially installing or conceptuating your pumping group, as the material of your part or of the part you test will not change through the lifetime, most often not change through the lifetime of your system. What can change through the life of your system or in your factory is the surface contamination. And this has a similar effect. So when we consider a clean part, it has a decent outgassing rate, let's say like the stainless steel part, but every contamination, let it be additional particles, let it be humidity, water or oil remainings, residuals from the processes before your leak detection process, all these contribute to the outgassing rate or the pump down time you will face. And this is also not so straightforward as when you say we have oil remainings on your part. It totally differs if you have just one droplet of oil at one particular position, or if your whole surface is covered, because this all influences the total outgassing rate of your system. When we now want to look also when we install the filler material out of aluminum, compared to before, the same volume decrease and surface increase, but now with aluminum, you see here that it's for the lower pressure limit, again, a very, very high increase in time again, while the upper pressure level is reached faster again. So it really depends on the materials you use to fill the free volume in the chamber, if you want to improve your performance of the system or not. And talking all the time about desorption rates. So these are, when we're talking about the simulation, are always considered after 1 hour. And the unit we apply here is millibar times liter per second per square centimeter. So here comes the surface of the part or of the chamber into the game. In a typical industrial application, we see outgassing rates in the 10 to minus 7 millibar liter per second per square centimeter range. But you see here it can differ. When you choose aluminum, for example, it's more in the 10 times to the minus 6 range. What we've also mentioned before, oil remainings can increase your pump down time due to outgassing and the choice of your filler material also. What you can improve further, if you see a big surface problem here, is a higher surface grade, which will decrease the outgassing rate. For example, if you have a standard stainless steel surface, you can improve it when you electro polish it or glass bed polish the surface. So these surface grade increases will decrease the outgassing rate and will improve your pump down time. But in the end, if you face a decrease in pump down during the production and you can correlate it to dirty parts, a better cleaning of your parts will improve your pump down time dramatically. Now to the last part, the pumping unit. Here you are to the components, let's say. It's not only about changing a pump, but also to change, for example, the piping diameter, which we will start with, which is also something you can do when you're facing problems, let's say right now after the setup was installed. So we see here again the example from before, the empty chamber and a loaded part made of stainless steel, because it's easier now to understand here. And when we now exchange the standard DN160 piping in this example through a DN200 piping, so we increase the piping diameter between the pumping group and your leak detection chamber. What we'll see here, clearly we have now a higher volume to be pumped down due to the piping, so the initial pump down curves are shifted to the right. The influence on the upper pressure limit level is not so big. You see here it's only 0.8 seconds, but for lower pressure limit, it really displays a very good increase. 56 seconds versus 48, or 53 versus 42. So roughly 20% increase in pump down time to reach the lower pressure level. This is due to the lower conductance losses you will face. In this pressure regime, where we're not having laminar flow in the pump down, the diameter of your piping comes more into the game. So it reduces the capability to suck out the air or the gas from your chamber much more than the length, or it increases for sure your performance when you have a bigger diameter. So what you will achieve with this is a faster pump down to final pressure. And so one could shortly summarize: an increase in piping diameter will result in a faster final pressure. But that's not only everything you can do. Change of piping diameter is one thing you can do for an installed setup. And if you have the place available, you can also think of installing another backing capacity in your system. We have talked about the 2000 cubic meter roots pump and only 600 cubic meters in the backing stage. When you increase the backing capacity, let's say to 900 cubic meters, so by adding another pump, you change the pumping ratio between the first stage and the second stage to more to better performing value. Like you see here, we have a drastic decrease in pump down time at the upper pressure level. So you reach the same level much faster because you have a higher suction speed in your backing stage, but also you need slightly more space. For sure, you also need more power as you add another backing pump, but overall, you result in a faster pump down time, which is particularly true for the upper level and also for the lower level, but not to the same extent. And this is summarized: higher pumping ratio goes hand in hand with a faster pump down overall. So that's the situation we have faced so far, or described so far in the last slides. What you can also think of in a retrofit, for example, to not only add another piping diameter or to add another backing pump, you can also think about changing the complete pumping unit of your system. But to exercise this in detail here would be too long for the scope of 45 minutes. So if you think about retrofitting or improving your pump down capacities of your system, my colleagues and I, would rather be happy to support you here with our knowledge to estimate the right pumping group for your particular leak detection problem. This is only the part which considers so far the chamber evacuation, but you can also optimize your pump down time or your overall process time when you spend some thoughts about your part evacuation. Because so far, during the initial pump down, before filling the part, often the part evacuation is done in parallel. So the pumping of the chamber lasts much longer than the pump down of the part, because the inner volume of the part is much smaller than the free volume of the chamber. But in the end, after a successful leak detection process, you have to clean up your part again from the helium which you inserted. So at some point, the pump down time of the unit you test is also important, not only for the contamination reduction, but also for your overall cycle time. And here we want to show you now what the influence of the piping diameter between the vacuum pump valve and the part here influences your overall system performance. So starting with something quite common, we have a DN6 piping of 0.5 meter between the angle valve to the backing pump. Oh, the presentation is gone, Jonas.
I see that too. I think it's opening again. Okay, here we are. Let me just share the screen again. Sorry for the short delay. Was it this one here, Philip?
It's okay. We just click fastly through. So again, we have the DN6 piping of 0.5 meter between the angle valve to the DN40 piping, which goes to the backing pump, which is in this case 100 cubic meter per hour single stage RVP. And what we are seeing here is for one time the suction speed curve with the black line showing you the reduced suction speed due to conductance losses induced by the piping. And the bigger graph in the back is your pump down curve, pressure versus time to reach 1 millibar for the filling of your part. What you see here also in the upper left table is the time to reach 1 millibar and the volume of the piping of this 0.5 meters of the DNX piping. And if we increase the DN from 6 to 8, we see a very huge decrease in time. So 63% less time is needed to reach the very same pressure of 1 millibar. But on the other hand, you also have an additional 86% of volume when we only consider this 0.5 meters. For sure, there's more piping in the complete system, like the connector to the venting valves, to the helium filling, and to the pressure release. But this is not considered in the calculation or in the additional volume here, only the direct connection between the pipe, the pump, and the unit under test. So we see here directly we have a faster pumping, but on the other hand, the higher volume. When we exercise this, we see to the next level with the DN10, we see even more increase here. 82% less time is needed, but 193% more volume is needed to reach this green curve here. So you can also consider when you say, okay, I don't need to reach 12 seconds. I have 30 seconds time, but when I increase my diameter, I also decrease the pressure I absolutely reach. And this helps us in cleaning up the inner part to reduce our helium contamination. Let's say I have 100% helium inside and evacuate down to roughly 1 millibar and fill it with air and then open the connector in my chamber. Some helium can exit my part and it goes into the system. Now, when pumping down lower, half a decade, so we have half the concentration which enters my system, which is of advantage considering a helium contamination of your system. On the other hand, clearly you have to consider it's a higher cost because for this volume increase here, you also have to fill it with helium during the pressurization of your part. But also this pump down time improvement here allows you in total to reduce your overall cycle time of your leak detection cycle. So it might be of advantage for you to consider a higher diameter to make your overall leak detection process shorter, which might counterbalance the slightly higher cost due to more throughput. And also what you can see here again, and which is one of the reasons to avoid the helium contamination, is the lower end pressure you can reach in the same time. But that's only one way how you can reduce the risk of helium contamination, Jonas. What do you also have in mind when you're talking about helium contamination risks?
That is totally right, Philip. Thank you also for this part on the evacuation and pump down things that we need to take care of. But yeah, speaking about tracer gas contamination and possible ways of reducing the risks for that, the first one you can see here on this slide is pressure steps and also the implementation of a gross leak test before the actual test. So that means whenever you have a test object that you want to pressurize with, for instance, 20 bars, yeah, and you want to make sure that you do not have a helium contamination in your chamber, you start with applying a very greatly reduced pressure on this test object. So instead of working with 20, you, for instance, just go with half a bar and check for any gross leaks of your part. And by that, you avoid that if you put the full pressure on it, that you have a huge contamination in your chamber. Another thing that is that you can do is the so-called post-evacuation So the longer you evacuate your test object after the actual test is done, the less gas, of course, stays in there, and the lower the chance is that you contaminate your chamber and your test object. Also, one important thing is the location of your leak test system in the factory. So there are certain production facilities where there is a huge level of helium anyway in the surrounding, or doesn't need to be always helium. It could also be hydrogen, which, for instance, is emitted in the electrical charging of electrical forklifts. So whenever you choose the location for your leak test system, you need to make sure that there is not a large amount of the tracer gas that you would like to use later on in the surrounding, because this will have a negative influence on the background signal that your leak detector is showing. Also, the environment of the chamber itself is quite important. So there's one thing that you can implement into your system, which is a purging of your chamber after the actual test is done. So instead of just evacuating your test object and your chamber, you additionally purge it with a purging gas, such as pure nitrogen, for instance. And you try to reduce the amount of remaining helium there, or tracer gas. And also the tracer gas concentration itself, as Philip already said, the more you lower your tracer gas concentration, of course, the less tracer gas remains in your chamber after the test is done. So much speaking now about tracer gas. There is one more question that we have for you, which brings us to the next poll. Philip, if you could be so kind and open it. Yeah, thank you.
We have talked about tracer gases so far, and also about concentration. So we would like to know which are the tracer gases you commonly use. Is it 100% helium? Is it a diluted helium? Other concentrations, 50, 30, 20, 5%? Is it, for example, a forming gas, 5% of hydrogen and 95% of nitrogen? Or do you directly measure refrigerants, or do you use other tracer gases which we have not mentioned here?
Yeah, and already 60% of the audience has voted so far. Thank you for your feedback.
I think we will give you another 5 seconds while we close the poll. Thank you for this. And yeah, the result is that 60% of you use 100% helium, 30% of the voters use diluted helium, which counts up to roughly 90%, and the remaining percents are more or less others, 5% refrigerants, and only 2% of forming gas.
That is, quite clearly into the direction of helium.
Yes.
Okay, so that is good that we were speaking about helium in the beginning. So thank you for your feedback. And then I will continue now with the test part itself. So we spoke now about the filling of the test object and the tracer gases. We spoke about the evacuation, and now it is all about the actual leak test itself. So before we take a look at that, we should need to consider again, what are the actual expectations that operators or companies and customers in the automotive industry have on a leak detection system. So usually what is most important is a high throughput, and therefore at the same time a required high process safety. Because as we mentioned in the beginning, usually these machines have a very large amount of test objects that they test during the day. And therefore we need to assure that the system has a very high uptime. So therefore the process needs to be safe and reliable itself. For this, it would be helpful if the test system is self-monitoring and comes with the right robustness, and also an error diagnosis as well as a data analysis, which ultimately require a service network, are important for leak test systems. Yeah? And you can see here on the right side that this is just an extract of a measured leak rate, and you can already see here that you need to consider many things for this. So there are different test points, different reading times, different values that you need to consider. And in the next following slides, we would like to go through each of those with you to explain you the individual requirements for the test. Okay, so in the beginning, you need to first of all select the right product for your leak test system. Usually with a high throughput in the automotive market, we are therefore talking about a modular leak detector, which can be integrated into a system and which is communicating with an external interface or with an external PLC. So in our case, that this is the ASI 35. This is our modular leak detector. And you see on this slide that it comes with different inlet ports, which are resembling different test modes. So you see here in the top, there is a sniffing module. Then you have a high sense mode, which runs with DN25. And you have a normal mode with DN16. And also on the right side, you see the gross leak mode, which can be used, or with this port is used at the same time for the backing pump. And the backing pump is something that these modular leak detectors usually require because they have a turbo pump, a split flow in them, and they cannot compress the air against the atmosphere. So they require a backing pump. Yeah, so after you have selected the right product, you need to think about in which test mode you would like to operate. And this is usually dependent on the test object that you have. So on the left side here, you see some typical examples from the automotive industry. You can see here a fuel tank, a battery pack, or a turbocharger. And of course, depending on the quantity, on the dimensions, and also on the leak rate that you would like to test, you then need to select whether or not you want to test in the high sense mode or in the normal mode. And you can see here on the informations here that those have some differences, mainly regarding the helium pumping speed that the leak detector is offering. So in the high sense mode, you have the larger diameter, so you have a higher suction speed. And in the normal mode, you have the smaller diameter, so you have a suction speed which is approximately reduced by by a factor of 3. Also, one important information that you can see here on this slide is the maximum test pressure. So this is the pressure that you need to have in your chamber before you open the valve to the leak detector. And those are different for the high sense and for the normal mode. You see here 0.2 millibar for the high sense and 1 millibar for the normal mode. So this is something we always need to have in mind and also need to consider in the layout of our leak test system. Also here you see several different contributing factors which we all need to consider. This is just an extraction, I would say, of the different factors that need to be considered when you are laying out a leak detection system. So whether you are talking about the helium concentration, the full or partial flow, or the usage of a booster pump, your chamber pressure and your chamber volume, the test mode selection and the response time, signal to noise ratio, and the maximum test pressure. These are all factors that need to be considered. Yeah. And just to explain this here on this slide, the signal to noise ratio, whenever we refer to this is what we understand is the relation of the leak rate that your leak detector is measuring and the background signal that you have. So when you have a background and you have a leak rate, those two put into a relation. That's what we call the signal to noise ratio. Okay, so we see there are lots of different things we need to consider. So let us take a look now how the, let's say, average test setup looks like. So usually when you lay out a system, you start with your test object, which in this case here is apart from the rack industry, a heat exchanger plate. And this is the test object that we usually put in a vacuum chamber and connect with a pressure gauge, because of course we need to know what is the pressure that we are having in this chamber. After we have done that, we need to think about our tracer gas supply. And you can see that here on this slide. In this case, we have selected helium, which comes in a bottle, which is connected with a valve. We have a valve for venting. We have a vacuum pump to evacuate the test object. We have a relaxing valve and also a pressure gauge to maintain an overview of the pressure we are applying on our test object. So after we have done that for the tracer gas, we need to take a look on the leak detection side. As we said, the ASI35 comes with different ports, so you can see here all the different connections that it offers, in addition to the backing pump that is required. And then last but not least, we need a pump to evacuate the chamber to get the right pressure in there. And here's already one thing that we can see what we consider as a first mistake. Here we use the backing pump of the leak detector also for the chamber evacuation. And this is something we usually do not recommend because we want to avoid that any kind of tracer gas is defunding into the leak detector back through the backing pump. So what we recommend is a setup like this. We use a separate pump for the chamber evacuation and a separate pump to back the leak detector. So this is just a safer side, and we are sure that we do not have a tracer gas contamination in the cell. Okay, so if we take a look at the procedure, we usually start with evacuating the chamber, while at the same time the leak detector is running and backed by the backing pump, valve is still closed. After that, we evacuate the test object, or actually it's not after that, it can actually happen at the same time. And then the test object is pressurized with the helium. So you can see that helium is applied. And now we are already at the first example that we would like to show you, which is called the partial flow. So in this example, you see that if there is a leak, the helium is sucked out of the chamber by both. On the one hand, by the leak detector, and on the other hand, by the vacuum pump. So this means that we have a partial flow into both units, and this has, of course, both advantages and disadvantages. On the one hand, of course, you have an increased suction speed for your leak detector, because usually in the normal mode, for instance, you have this 1.8 liter per second. When you have a backing pump with 20 cubic meters per hour, this will be an additional support and this will increase your overall suction speed. So, of course, you not only have a faster evacuation, you also have a faster response and a faster recovery time of your leak detector. And this in general, of course, has a better, a positive impact on your process stability because you reduce risks of helium contamination, for instance. On the other side, if you have this partial flow, it means that not all of the helium is detected in the leak detector because a significant amount of the atoms will be pushed through the backing pump and will not be detected. And this, of course, has a negative impact on your signal intensity. So therefore, when you use a backing pump in the partial flow, both your background and your signal to noise ratio will increase. So this is something rather negative. And also depending on the relation between leak detector and backing pump, you will have a higher machine factor. And this is one of the this is actually the last question that we have for you, which is on the machine factor. The question is, what do you consider as an acceptable machine factor in your production? So you can see here 4 different answers. We have less than 150, less than 100, less than 50, and less than 25. Philip, I believe for us, the standard setting, or what we say, is a factor of 100. Is that correct?
Yes, so less than 100 is for sure should be reached. And when we have a short look at the real life voting here, also less than 100 is quite common. At the moment, it's not decided if it is below 100 or below 50. They're taking sometimes again head-on-head race.
Quite well distributed, as I can see.
Yeah. Well, we give you 10 more seconds to vote here. This time only 50% have voted yet, so not so much than before. Still, 50% is more than nothing. And well, let's close the poll. And 40% of the voters stay below 100, 30% below 50, and 23% below 25. and the
Perfect.
remaining
So
below 150.
okay, great. So thank you for your feedback, and this just goes along with what we consider as an acceptable machine factor. So thank you for that. Now that we have spoken about the partial flow, we want to show you, of course, the opposite method, which is called the full flow. So in this case, of course, the test object is also evacuated and then pressurized. And then in the next step, you will see that the helium is going 100% through the leak detector. And then, of course, this has the same advantages that were the disadvantages of the partial flow before. So now you have a much better intensity, but of course, a lower suction speed and therefore a slower response time. Yeah. And one thing to optimize this in the full flow is something that you can see here on the next slide. This is the addition of a turbomolecular pump right on the chamber and directly in front of the leak detector. So this has a great advantage that 100% of the helium atoms will be pushed into the leak detector. And also you have a very high suction speed of the leak detector because the turbo pump sits directly on top of it and will support it significantly. So what we can say to the advantages of the full flow and also of the booster pump is basically what I just said. You have the advantage that all of the helium will be detected in the leak detector and you have a very high signal intensity. However, if you use the whole thing without a booster pump, you will have a lower helium suction speed and also a slower response and recovery time. But what we can assure you and what we usually always consider when we have a high cycle time requirement and a leak rate that is in the right ratio, then we usually always consider the usage of a booster pump. Of course, it has an additional investment cost at the beginning and the layout, but we would say the great improvement on productivity enables that there is a very fast return on invest for this one. Yeah, so just to summarize the differences between the full flow and the partial flow, I think we can do this pretty good with this chart here. So you see the leak rate in this red line. You see on the left side here the level of the full flow method, which basically tells us the intensity of the signal. And you can see that this intensity is higher than the intensity in the partial flow. The advantage that you have in the partial flow, however, is the response time. So you see here these vertical lines are the response times, and we see that those are much quicker for the partial flow in comparison here to the left side for the full flow. Yeah, so this is basically a good summary of the pros and cons of the different methods. So now that you know about that, the question is, when do you choose which method, or when should you choose which method? So what we always recommend is that whenever you have small chamber volumes and your time to test is not that critical, and also when you have leak rates in an acceptable factor, so we would consider here small leak rates smaller than 1 × 10⁻⁵ millibar liter per second, then this could be a good opportunity to work in the full flow because you have a higher intensity. Of course, it takes a little longer, but your process is not that time critical, so it's a good choice, yeah, and it enables you to get a good background, low background. On the other hand, the partial flow should be used whenever you have large chamber volumes and you have not that much time to test and you want to have a short cycle time. Then you necessarily need to run in the partial flow or at least have the usage of a booster pump. When your machine factor is acceptable, yeah, then you do not need this additional booster pump and you can just operate the leak detector right next to a normal vacuum pump. And you will end up actually with a medium background and a medium signal to noise ratio. Yeah, and then the last option that we have is the booster pump that you can use for larger chamber volumes and time critical tests. The booster pump itself, when you imagine that you have the leak detector and the booster pump on the one hand and a separate vacuum pump in a partial flow on the other hand, if you have both of them in relation, you will have a better machine factor than without a booster pump. So partial flow without a booster pump has a worse machine factor, and you can improve this factor by the addition of a booster pump. Yeah, and also ultimately you will have a higher signal intensity and also a lower background than in the regular partial flow. Yeah, so one thing that we will add to this is also later on 2 slides, but there's one thing that I would like to emphasize here again. But first of all, we would say that we should take a look at the takeaway for today's presentation. Yeah, so general advices and best practices. Philip, yeah, you can go ahead with the first point.
Yeah, thanks. Yeah, what we said before, or what I presented to you in the beginning, is the process conditions, what I summarized as the free volume and the surface condition. These can heavy influence and also counteract each other, especially the surface contaminations. If you have oil remainings, this will reduce or enlarge your cycle time of your pump down.
Yeah, the second point is regarding the piping, and this is something we always recommend to you. Bring both the leak detector and of course the vacuum pumps as close to the chamber as possible. I mean, we usually know that we want to avoid conduction losses, but especially for the leak detector with the DN16 or DN25 connection, it is important to bring it as close as possible because every additional centimeter will have an impact on your suction speed. So this is really important.
Yes, another slogan which you can keep as a takeaway is keep it clean. So the tracer gas pollution in the surrounding or in your part, so the thorough cleaning of the part itself is very important to reduce the contamination in your chamber.
Yeah, also the test mode is something that needs to be considered quite importantly because depending on the test mode that you are working with, you can have an influence on the contamination risk of your analyzer cell. So that means what we recommend, if it is possible for you to work in the normal test mode with the ASI, then we recommend to go for it. If you are, however, required to go to the high sense mode, then switch to the high sense mode. But the rule of thumb is work with the normal mode wherever possible.
And if you also want to improve your cycle time, Jonas also presented you the partial flow. For sure, you can, for pump down, increase the suction speed of your pumping group to no limits, but then you will have a problem with the with the background level also. So the response time and the background level have to be carefully evaluated to properly set up your process.
Yeah, and then also in addition to that, to the partial flow, you can always use a booster pump to reduce your response times and improve your machine factor in the partial flow. And as I said before, one thing that I really want to emphasize again, because now we told you in 45 minutes lots of different things, and I think it's hard to get a full overview of the whole dimension of the leak detection world, especially in the automotive industry. So what we want to emphasize is that please feel free to get in touch with us when you have questions regarding the layout of your system, when you need technical consultation, or just have questions on the topic in general. So we are there for you, and we are happy to support you in those regards.
Yes. And now I think we will want to thank you for your attention and for patience now for the 48 minutes. And now let's see what for questions have we received in the last 48 minutes. So one question, Jonas, which options do you have in general of self-monitoring leakage testing systems? What do you think? What for options do we have?
For self-monitoring, could you repeat the question, please? Sorry, Philip.
Which options do you have in general of self-monitoring leakage testing systems?
I would say there are several things that we can consider in these regards. The system itself usually, of course, is operated with a PLC. Yeah? So this is something we do not provide, but we are the experts on the different components for a system. So we provide the pumps, the gauges, the leak detector, and so on. And these, depending on the choice you make there, for instance, the vacuum pumps, they have several options of self-monitoring and preventive maintenance. Also, the leak detector has several service intervals, and so on. But I would say the overall self-monitoring is something that is usually done by the system builder and the PLC.
Yeah, he could, for example, track the pump down times you need to reach a certain pressure level, which can indicate contamination on your surface of the parts of your surface. When they're getting more dirty, then the pump down time will enlarge. When the background level increases over the time, then you have something like a leak somewhere in your system, which continuously improves, not decreases, your cleanliness of your system. So there are many things you can read out directly from the parameters or indirectly from the process itself.
Okay.
Another question is the meshing factor similar to the so-called sensitivity? If yes, please explain this measurement.
Okay, so that is not the case. There's a difference between those two factors. If we, let's say, take a look at this slide here again, you see here the vacuum pump has a suction speed, and of course the leak detector has a suction speed. And if you operate in partial flow and put these two suction speeds into a relation, yeah, then this is what we call the machine factor. And if we speak about the sensitivity, that is more what we mean the sensitivity of the leak detector itself. So this is the same thing as the signal to noise ratio. So when you have a underground in the chamber and you have a leak rate that you measure, then this is the sensitivity. I can show you this again on this slide here. So you see, for instance, a difference here in the 1 × 10⁻⁹ range. This is the background that the leak detector is seeing, and the sensitivity is the relation of the leak rate that it is then actually detecting. So it's a different thing, the machine factor and the sensitivity.
Okay, thank you, Jonas. And the last question is, what is better to your consideration, to install the mass spectrometer directly on the chamber or into the piping of the chamber pumps?
Are you referring to the mass spectrometer of the leak detector, or?
And I think the mass spectrometer is here meant with the leak detector itself. So
yeah.
the inlet part of the leak detector.
Yeah, that always depends on the setup, I would say. But usually, when you go with the hard vacuum test, yeah, then you should have the leak detector as close to the chamber where you would detect or where you want to detect your helium as possible. Yeah. So if your test object is in the vacuum chamber, I would go with the chamber. Yeah.
Yes, and also if you consider that you have, for example, a two-chamber system with one pumping group and one leak detector, it wouldn't make sense to install the leak detector onto the piping of the pumping group, because this can change to evacuate the other chamber already when you're still measuring the first chamber. So it depends on your setup where you should install it, let's say.
Yeah. But yeah, good point. And I also get the point that in some cases it can make sense to connect it to the piping of the pumps, because, for instance, when you work in partial flow, then of course you use the suction speed of those pumps. So we can understand that, but we would need to take a look in particular at the setup you are referring to.
Another question came in, which is, what is the use case of the relaxing valve? Maybe I try to answer this. So if you have a testing pressure of 5 bars in your part and you want to evacuate it again, no vacuum pump can really live with the inlet pressure of 5 bars. So you first have to release the pressure to atmospheric conditions to 1 bar, and then you can use the vacuum pump to pump down to your defined pressure before venting your part with air or from your venting line. So it's more to save, to protect your pump from an overpressure, and also could be used to feed back the overpressure into a recovery system. So the 5 minus, so the 4 bars overpressure are directly filled into your helium recovery system again, and then the pump pumps down the remaining volume to 1 bar also into the system.
Okay, thanks, Philip. And there's also another question. Why is the response time of the partial flow method so much lower than the response time of the full flow method? So I think the question is referring to this slide again, to this one here.
Yes, so the response time is calculated as the volume divided by the effective suction speed. And in the full flow, you can consider also only the suction speed of the leak detector, let's say 4 liters per second. And in the partial flow, you add 20 liters per second in addition. So you have a total suction speed of 24 liters per second, which is a factor of 6 higher. So the response time is also a factor of roughly 6 shorter. That's the reason. You have the same volume you evacuate, but you have a much higher effective suction speed, which reduces your time needed to reach the same response level.
Okay, perfect.
And I think
so I don't see any further questions. So there's one more coming in. Will there be a training in which we will explain the different inlet ports of the mass spectrometer or of the leak detector? Actually, maybe I can take this away. We have several different, let's say, technical documents on the ASI 35 available, which we can provide to you. Also, if you have the need for that, we can also have a call together with you or a conversation in which we go through this in detail. Yeah, but in general, we have the difference between the high sense and the normal mode, and just different inlet pressures and different suction speeds for the different ports. Yeah, but we can reach out to you after the presentation and come back to your question if you like.
So with this, I think we have answered all the open questions here. Again, from our side, thank you for being our guests today. I hope this was a valuable time for you. If you have any questions, please feel free to reach out to us also afterwards. We were happy to help you.
Thanks a lot also from my side. Thank you for joining. Thanks for your attention. Have a good day.